And yeah, for the fourth talk, we welcome Rohit Sharma again, and this time to speak about solar and heliospheric physics with the SK.
Oh, I might have got the same one. No, we didn't. Whoops. Give me one moment. Got to close the other one. Yeah, classic problem. All right. I can just find where the thing is. That'd be great. What is this? We'll just go there. Yeah, over there. Okay.
Okay. Yeah. Thanks. Yeah. So I'll talk about like in general the solar and heliophysics science with SK, and this work has been sort of like motivated, or at least we are starting to think about doing SHI with SK based on our this recent development, and there is also the construction which is also driving this particular effort. And so I'll basically give you a brief overview of what are the things probably we can expect in SHI with SKA. Okay, yeah, so just again a little introduction to the sun, especially the small scale things which are happening on the sun. For example, now we have a sort of like a observatories which are revolving around sun and providing sort of like unprecedented details in terms of the spatial extent or the scale over which the emission is or energy releases are occurring on the sun. And you can see like the zoomed in version of these ultraviolet images suggest there's a lot of time variability, there's a lot of these campfires, this type of things which are sort of like occurring at a very small scale. And so we need to sort of like understand them in terms of their origin, and of course the radio wavelengths help in that particular aspect, and the underlying physics or underlying mechanism which is actually deriving all this is most probably the the magnetic reconnection. It's a fundamental mechanism which is accelerating the particles. And you see the effect of those particles, accelerated particles, in different radiation wavelengths, including X-rays and radio. And the most common problem, the coronal heating problem, is sort of like is attributed to these magnetic reconnection events happening all the time. So problems like these must be sort of like addressable with, for example, like the observations with SK, let's say. And when we talk about sort of like the radio emission in general from sun, they span the great diversity in frequency axis, in time, in temporal axis, and in the flux density axis. So here I basically show you the plot of the flux density versus frequency on the left, and the red box actually shows you the frequency range of SKA. And you can see on the top two curve, the active sun and quiet sun, they span like many orders of magnitude in flux density, especially at the low frequency end, where we also have MWA operating there. So there is a lot of variability which actually comes from intrinsic emission at radio wavelengths. And with such a wide frequency range, one can actually build a very good model of solar corona. which is something to be looked after. And in terms of like emission mechanisms, so what are the emission mechanisms at these particular radio wavelengths? The right graph actually shows the dominant emission mechanism at different frequency, and you can see like at higher frequency range, let's say above 1 gigahertz or something like that, the gyro resonance or the Bremsstrahlung and sort of like they dominate the magnetically dominated systems, and at low frequency the plasma emission sort of like it dominates. So again, depending on the frequency range, you can actually try to study different types of emission mechanism using radio wavelengths. In terms of morphology, as you go towards the higher frequency, then you are more closer to the solar surface. The optical depths are quite low there. And you actually begin to sort of like resolve out the solar features, for example, like these active regions, coronal holes, different types of features present on the solar surface. And as you go towards the low frequency, you basically probe the solar corona. And the solar corona is intrinsically diffuse and comes from different types of emission mechanism as stated. So you can actually understand like a lot in the morphology. Right. But the challenges at radio wavelengths are there. So the dynamic nature of sun that we have seen with MWA is like it changes over the sub-second scales. So you need to basically capture this variability to comment anything on the emission. Again, the flux calibration and polarization are particularly important, and they actually provide a lot of challenge in analyzing the data. And as we see from the last talk about the triggering mechanism, this is very important to sort of like capture big solar events, because then they provide the context with the multi-wavelength observations. And the intrinsic complexity in the emission mechanism, especially in the low frequency range, also is one of the challenges. Sun being very bright is sort of like limited by the self noise. And the self noise, we need to sort of like beat that self noise somehow to basically to gain more information. And the plot which is shown on the right, it's the work by John, where basically it's a first-hand calculation on basically the on-source and off-source region, the dynamic range, and for different elements on the x-axis. So you can see the on-source noise. If you have the larger number of elements, it sort of like saturates. So if you basically go from, let's say, like 256 elements to 512 elements, there would be marginal increase in the dynamic range. So this is one of the this is sort of like intrinsic challenge in sort of like the heliophysics cases. The solar science which will be enabled by SK would be quite large. One can sort of like study the coronal heating properties which are close to the surface of the sun. As you go above, then there could be you could study the solar atmosphere, including the waves and the propagation of different types of phenomena like coronal mass ejection, shock propagation. And if you basically study the quiet sun part, which actually has a lot of information about the density inhomogeneities which are present in the solar corona, you can build or like a scattering models of the solar corona, and as a function of like time, how does the density and homogeneity change, or depending on the features which are present underlying the sun. So there is a lot of variety of these science cases which will be enabled. The current best radio telescope that we have, which observes sun, they are mostly non-solar dedicated. The EOBSA, which is operating at 1 to 18 gigahertz in the high frequency range, and of course in low frequency we have MW and LOFA. If you go below the ionospheric cutoff, then we have space-based radio and spectrometers which actually do that. With the SK, we will have more number of stations, and of course better time and frequency resolution, which will actually provide an improvement over existing facilities, especially with the larger extent of the array. We will get a larger angular resolution on the sky, which will be quite useful for heliophysics cases. And all this would sort of like enable even more high sensitive images with a better fidelity and with better frequency and time cadence. So in the timelines, even so, the SK timelines are very well known now. So with A star with sort of like 144 like stations, you would have the first operation thing. And subsequently, like in the development, you would have some solar data anyway. And one of the eye-opening moment as it is the first station from the SK low, and this is basically the all sky. You can see the rise of the Milky Way. This was quite exciting, and as the Milky Way sort of like sets, there are some the LMC and other radio sources which pops up, and then you have sun. And as soon as the sun comes up, it actually saturates everything, so everything becomes dim. And as the sun sets, then again the galactic plane brightens up. So yeah, so this was quite exciting to see this particular for the first time. And there are also sort of like efforts in basically doing solar observation at SK mid with Meerkat. And with Meerkat at high frequencies, you get basically high angular resolution. So you can actually see very nicely the correlation with other wavelengths. For example, like you can see the bright spot there would be associated with some active region there. So Dev Jyoti is sort of like leading this effort with the observation with Meerkat, and it is producing some very nice images. In addition to this, there is also importance of simulations, because we are sort of like in a strong signal regime, and the noise characteristics in the images can be simulated. And so for this, the importance of the simulation lies, and we can actually study the artifacts and the manifestation of different types of noise sources in the image plane. And it is, of course, when the observations are around, then you can actually use them to debug and develop new algorithms. So for this, we actually we developed this pipeline called Karabu pipeline. It's a SK simulator based on the Oscar, the SK low simulator in the low frequency, and the Rascal in the mid frequency. And this is a sketch effort, and please have a look if this might be interesting to you. The workflow is very similar. You have sky model, telescopes, and observation modules, which actually you can actually provide in inbuilt the MIT and Gleam catalogs to simulate the sky, and then you can also supply different types of beams, and then you can simulate your your observations. For sun, we basically take a simplistic model, which is derived from MHD simulations, and then forward modeled, assuming sort of like a thermal Bremsstrahlung emission optical depths. And then we basically pass these to our telescopes like MWA, SK low, Meerkat, and SK mid. The notable feature is that for SK low and SK mid, the maximum baselines would be quite large, and MWA would fit somewhere there in that particular little circle in SK low, and similarly Meerkat. So you would get like a very long baseline, which would have which would provide high resolution, for observing different types of phenomena, especially the flares. They are very, very compact sources. So we are really, it would be really interesting to see the morphology of flare with such a high resolution. Some simulated images at SK mid, let's say, you basically gain on the number of elements, and then also on the resolution. So with SK mid, you have a better PSF as compared to the current MeerKAT, and similarly for SK low. For SK low, since the maximum baseline is around whatever 65 kilometers, you basically gain on resolution. So you basically try to you basically have the fine structures which are present on the solar disk, and it really would be quite interesting to see those structures. Right. And if we sort of like translate this particular the resolution to some physical scale, one can actually already try to see, for example, with SK low, it would span anywhere between like 2 megameter to 13 megameter, which would actually sort of like the physical scales would correspond to magnetic loops, for example. So you can maybe try to we'll get some emission, some loop emission or some curved emission from these particular loops, and from SK mid you would have even finer resolution. So you can do studies, for example, like turbulence and stuff like that. So, and also you would get a better better spectrum for different types of events. So it will improve your fitting, and subsequently your estimation of the plasma parameter of that particular phenomenon which is happening. So in a way, so with larger baselines and larger number of elements, you would improve. And basically, in the summary, I will just say the SK will enable a lot of science cases, which will actually improve our current images and all. For IPS especially, for example, these sub-array modes and beamforming mode would be quite interesting, because you would actually would be able to track CME at further distances from sun. And with simulations, we are trying to currently understand the instrumental characteristics. And of course, the experience of MWA will be vital to design SKLO observations in future. So that is very much there. And yeah, so I'll stop here.
We have questions for. Okay, so then we will. Yeah. So for the last talk, we will welcome Angelika Waziewski online from the International Centre for Radio Astronomy Research in Australia. The title of the talk is Interplanetary Scintillation Science with the MWA. Okay, so sorry.
Hello, everyone. Hopefully you can hear me.
Yes, this is all good. Thank you.
Fantastic. And my screen hopefully is sharing as well. Great, cool. So hello, my name is Angie. I'm a PhD student at Curtin University, and today I have the pleasure of presenting some of the work that I've done as part of the IPS team in interplanetary scintillation studies with the MWA.
Yeah, one sec.
Sorry, go for it.
Because we cannot see your presentation for now. Just 1 second.
Oh, in the room. Yeah, that's okay. All good.
Yeah.
Stop sharing now.
Okay, we can go on. Thank you.
Fantastic. So IPS is the amplitude and phase scintillation of compact radio sources caused by turbulence and density changes in the solar wind, and whether these density changes are caused by small-scale fluctuations in the ambient solar wind or injected on the large scale by transient events such as coronal mass ejections and stream interaction regions, we will see that as twinkling galaxies. Now, historically, this phenomena was used to study the astrophysical sources themselves, as it only acts on compact sources. But in recent decades, we've used this phenomena now to actually study the density enhancements themselves, like the solar wind itself. So there's a couple of places around the world that do this kind of work. One of them is IC at Nagoya University in Japan, where they study the deviation of a source's scintillation to study this particular coronal mass ejection as it moves through the interplanetary medium quite far out in space. So this image on the left of the coronal mass ejection is quite close to the sun. It's around 32 solar radii away, whilst on the right we are looking all the way out to 1 AU. Now, I specifically mentioned the deviation in scintillation. That's the measurement that we use, the G level. And we pretty much just look at the ratio of the observed scintillation versus the expected scintillation of a source. So the observed is quite easy. It's just whatever the level of scintillation that source has at any one moment. But there is a couple of things that go into the expected scintillation of a source. One of it is source structure. It's specifically the percentage of the source or the source's flux that contributes to the scintillation. So 100% would be a completely compact source similar to a pulsar, rather like 50% source structure would be a compact core, maybe extended jets. And only part of it will scintillate. The next is solar elongation. So how far away our line of sight or how far away the source is from the sun. Our G level, the scintillation measurement, is an integration over the line of sight, but we are obviously most sensitive to the closest approach to the sun, where we're actually going through a lot more of that dense solar wind. So the closer you are to the sun, the more solar wind, the higher the level of scintillation. And then the next is actually dependent on the solar cycle. So the sun goes through about an 11-year cycle from minima to minimum, where at solar minimum, we expect low levels of solar activity, whilst at maximum, we expect a lot of solar activity. And that will actually change how we view our scintillation. So some of the work that I've been doing is by studying at what point, or like the shape of the solar wind, specifically where we have a turnover point, where we move from strong scattering close to the sun to weak scattering at further out in the heliosphere. And we see that at solar maximum, or in periods of increased solar activity, we have a spherically symmetric solar wind, where no matter the solar latitude that you're looking at or where the source is at, it will be spherically symmetric, equal around the whole way around the sun, whilst during periods of decreased solar activity, we see that it morphs into more of an ellipsoid shape with flattened poles, still reaching the same level as at the equator, which is something to keep in mind when you're doing scintillation studies. So how we got this data, how we got the data that I did for the previous work that I just showed, we've been taking multiple pointings, multiple observations around the sun every single day for a couple of observing periods now, and you can see a comparison between IC of their work that they did previously. So they also do daily observations around the sun. They're monitoring about 70 to 80 sources a day. Whilst with the MWA, thanks to its high sensitivity, wide field of view, we get around 2,000 sources per day. So we get a lot more fine-grained detail that we can monitor of more of that ambient solar wind as well. We're also comparing to other solar monitoring campaigns. So the purple circle is quite small, it's quite hard to see, are the heliopolarimetry guys that were just talking. So they're also looking quite far out into the heliosphere, but we look a bit further at about 0.5 AU away. And those inner rings that you see are current solar monitoring campaigns, specifically for the satellites, the Solar and Heliospheric Observatory at L1. These are common coronagraphs that look really close to the corona to look for CMEs. And we have data ranging all the way from solar minimum in 2019 to solar maximum, well, solar ramp up is what I say, and we're also observing for 2024, so even higher levels of activity that we'll be catching. So all of these daily observations were poured into the MWA IPS survey. So a couple years back, John Morgan and the IPS team released data release 1, where they identified over 7,000 IPS sources in the MWA's skies. This is the largest catalogue of known IPS sources to date, an order of magnitude higher than previous catalogues held by other observatories. But when I started my PhD, I was starting to go into new data, which required an all-sky catalogue of IPS sources. So I started working on data release 2, which is yet to be released, but we have identified now over 20,000 IPS sources. So an increase, another order of magnitude up in terms of catalogue sources. So with this survey, we now have a really good understanding of how each of these sources scintillate. We know its source structure. We also have multiple observations of every single source at multiple solar elongations, as well as this survey was taken over observations ranging from 2019 to 2021. So we also have at differing parts of the solar cycle as well. So we really understand how each of these sources scintillate. So from there, we can start looking at how they deviate in their scintillation to look for possible transients in our observations, but also the ambient solar wind as well. So the way that we do that is we make G-maps. So it's just measuring the G level of every single source in an MWA observation, and then putting it on a nice little color gradient. Now, the guys back at IC, they are only looking at G-level enhancements. So G-level is a proxy for the density in the solar wind. So an increase of G-level, so above 1, we're looking at a density enhancement, whilst if you have a G-level below 1, there might be a lack of density in that region. I'm interested in both because since we have such large density of sources, we can now start looking for rarefaction regions behind shocks that are traveling through the interplanetary medium. So I like having both as quite important. And with these GMAPs, we can make a GMAP for every single observation that was taken on a single observing day, so a single UTC day, to create a daily GMAP. Now, I much prefer working with these daily GMAPs rather than the individual observation ones, is when I'm looking for CMEs are quite big. When they are at the sun, when just in the coronagraph images, like really close to the sun, they can span of angular widths from 10, 20 degrees all the way to 360 degrees. They can be huge halo events, which take up a large portion of the field. And by the time they reach our heliospheric like distances, like we're all the way out at 0.5 AU, these shocks can be quite large. So by looking at multiple observations at one time, I can see structure that might be spanning over multiple observations that I might not catch if I was just looking at the singular observation GMAP. So I've looked through a lot of these daily GMAPs. I've looked through a lot of our data, and I've kind of been going on a bit of a transient hunt, specifically a CME hunt, trying to see if we have just nonchalantly captured a CME in our data when we were doing our daily observations around the sun. I have a long list of them, but obviously I can't go through all of them today, so I'm just going to go through 2 of my favorite ones. So the first is on the 7th of September in 2022. We're going to be focusing on the eastern limb of the sun. We're looking at the lower left corner. You'll see that there is this kind of stripe of enhancement followed and preceded by these lower levels of scintillation. It's a really nice structure that seems to be going all the way from the southeast, moving out to the east, and all the way, if we maybe had a couple more sources in the north observation, that maybe we've seen this structure keep going, but it's really strong in that south region. And what happened a couple days prior to these observations is actually the largest, well, the fastest CME ever recorded in humans' history, which is pretty fun. Thankfully, it was aimed away from us rather than towards us, but that also meant that Parker Solar Probe got directly impacted by this CME and recorded wind speeds of above 3,000 kilometers per second, so incredibly fast. So I have a quick video of this in combining both the C2 and C3 coronagraph images with, I'll play that again, C2 being the smaller ring and then C3 being the outer ring. And we see this really big CME go off, and then actually we see a secondary CME. Now, I don't actually think we're seeing this Labor Day event CME. They've called it the Labor Day because it was on the 5th of September that it was ejected. We see that the majority of the front of the CME, ignore C3 as well, being a little bit silly. We don't know why that happened. It's also not related to the big CME that went off. But we can see in C2 that the Labor Day CME happens to be more aimed towards the southwest rather than the southeast. There's a little bit coming out from the eastern limb, but we don't think that we've actually caught this one. We think that we've caught this secondary CME that went off just 2 hours after that large Labor Day event. From the same active region, it's just flared in a different way. And thankfully, C3 fixes itself after a while, and we can see that this secondary CME happens to be forming a bit of a shock that is traveling towards the southeast region. There's potentially a chance that the previous Labor Day CME is now being pushed or interacted with by this secondary CME, but I'll touch on that a little bit later. And the next event, which is my favorite, is because it's quite striking in the IPS data. We're now not looking at the east, we're now looking at the west, so to the right of the plot. And I'm showing 4 successive days of data. So the first day is the 4th of March. It's going quite fast, but it's the one that has absolutely nothing going on in the field. Maybe there's a small variations here and there, but no major structure. On the second day, we have the 5th of March, which is once again this really nice structured enhancement being followed and preceded by low levels of scintillation. So it really happens to be a shock moving through the interplanetary medium. And on the final day, on the 6th, we see that this enhancement has now moved and expanded and is now on the edge of our field of view, and it seems that it's gotten stronger. Now, this could be caused by the geometry of the event. Like I said, we have a line integration that's probing the density of the solar wind, and we're the most sensitive to the closest approach to the sun, and that obviously spans out a little bit as well. So this CME could be moving in a way that it is entering into a more sensitive region of our integration, which means that we could potentially see if it's moving towards us or away from us. But it's also moving quite slowly if we actually do the calculation of that solar wind speed. And rather than it being a single CME that's moving quite slowly, I believe it's some CME interaction happening all the way out in interplanetary space. So I'll show the C2 and C3 images again. What we actually see is a flurry of activity with lots of CMEs going off, jet-like CMEs going off, and multiple big CMEs interacting with each other. So originally, we see the first kind of big and like momentous and picturesque CME is quite slow, but it actually happens to be propelled by smaller but faster jet-like CMEs, which truly look like a jet. It seems to be pushing and coming out of that same active region and pushing it forward. And before this CME even has a chance to leave the C3 field of view, another bigger and even faster CME goes off, hitting it and ramming it from behind. So you can still see, it's hard to see, but like there's ripples in the edge of the C3 of that preceding CME as well. So what I believe is we're catching these CMEs interacting with one another that could be interfering with our plane of sky velocity that we're seeing in our IPS data. But it's super important to catch these events, as it's hard enough modeling how a CME evolves through the interplanetary medium just by itself. When you start adding other CMEs, other flux ropes, different density regions interacting with one another, it gets a bit difficult and a bit hectic in trying to understand their evolution, which is very problematic when we are coming up to a solar maximum phase where we're expecting to see multiple CMEs every single day. So it's really important to know how we can model them. So the idea of this work, the kind of like final goal for this work is kind of you scratch I'll scratch your back situation, where we hope to use magnetohydrodynamic simulations as well as flux rope simulations that are currently run by CCMC in injecting a CME into a modeled environment and watching its simulation as it evolves through interplanetary space, and then forecasting this model out until we can see what would we see if we could measure in G level in these data cubes. Now, these won't be exactly like what we would see in the MWA, but it'd be close enough. So the idea is, one way is we can inject CMEs to see if what we are seeing is being caused by that particular CME, but also run multiple simulations of that same CME to see which input parameters give us the best fit to our observational data. And with that, thank you all for listening.
Thank you for that, Angie. I guess, do you want to take up there?
So do we have questions for Angelica? Nobody? Okay, so I will thank again all the speakers from this session. Now we have a coffee break. You'll have to be back at 11:20 for the start of the next session. And thank you for listening. Yeah? Thank you.